I'm the founder and CEO. I've been there for a bunch of years. But one common theme throughout my entire career has been artificial intelligence and neural networks. In fact, when I started, it was an undergrad. I went to the Colorado School of Mines. I was in a mass spec lab, pyrolysis mass spec lab. And as an undergrad, I was engineering chemistry and computer science. I was using neural networks to actually categorize really complex samples. Pseudomonas xanthomonas classification using pyrolysis mass spec as input. Didn't think much of it, but then I went off Berkeley and I jumped into this world of protein folding and I tried to predict protein structure. We only had a couple hundred protein structures at that point, and now we get that each week. And one of the most important themes you're going to hear from me today is that content is everything. And if you don't have a lot of information, you're surely not going to be able to train these AI systems. But that time we didn't have much information, so I had to reduce the problem down to sub-problems. And we were focusing on things like secondary structural prediction, disulfide bond formation, and touch on that a bit more, surface accessibility, and other things like that. You actually can see we actually had 2 neural networks at one point. That's actually the early deep learning. We didn't call it that, but that's what deep learning is when you have multiple neural networks together. I then joined a software company by the name of Molecular Design. This company focused on chemical information management. And I, as an early application scientist, was applying neural networks on the chemical structures in those databases to predict biological activity. And we were using at that time the MDL key set, which is the numerical representation of chemical structures to facilitate rapid database search. But I pushed the company to make those exposed. And that was like really tough because the software company wanted to keep everything for themselves. And I'll come to that in a minute. I later joined ADMETox and we implemented a ton of infrastructure because we put in research computing. Believe it or not, they didn't have it. Some of you might know, I know Suresh knows of ADMETox. ADMETox actually was the parent company to ADMETox. I'm sure many of you know Metric. So Metric spun out when I was there. ADMETox did great combinatorial chemistry work and no research computing. So imagine on K2 place, it was all Macintoshes and we had to put in different infrastructure and then put AI on top of that. Wow. Amazing. People didn't even know it was there, but it was there and it was very helpful. And then in 2003-ish or so, we established a company, Certainty, and we've been using neural networks and a ton of AI, but also more importantly, the content that choose to train these. And we actually license the databases in that world. So that's about me. And I'd be happy to talk about any of these applications offline if you'd like. We will have more time later. There we go. One of the things I want to touch on though, and it's perhaps very relevant for you here, Pichia company. Open source in the software world, I believe, has truly changed the world. In the early days, we didn't really have much software at all to work with. I mean, I was doing my grad work with neural networks. I had to write all my own neural network code. I had to write my own scripting languages. I didn't have Python, but now all this stuff's available. And if you notice, using Changer for your if you notice, after 2015, it's been an explosive growth. I should say that this is the number of GitHub submissions, which kind of cute. I actually asked ChatGPT to write code for me to pull it out. I write this code. Now, well over 200,000 source code repositories at GitHub that you can just pull for free. And so everything we talk about today, you don't need computer scientists looking for you. You can hire a summer intern, put them on a laptop, and have them pull from GitHub, and they will get you up and going really quickly. So it's amazing how this has totally revolutionized the world. Let's talk about neural network. This is one type. It's called feed-forward. It's actually at the heart of a lot of neural network technology. And the fundamental point behind a neural network is the computational node. It's based on like a biological neuron in a sense. And it's a little decision maker. It takes a weighted sum of its inputs and fires according to some threshold activation function. It's a nonlinear decision-making entity. So when you start putting these in layer, you can start to create some really incredibly powerful tools. But at the end of the day, all neural networks are really doing is taking a series of input patterns and producing a series of output patterns. And it's your challenge to come up with problems to define what those input patterns look like. So it's just a string of numbers going in and a string of numbers coming out. Now, a neural network can be trained to be capable of doing just about anything that's represented in this way. When you provide an input and you stream it through and you get an output, you try to change the parameters in the neural network to produce what the output patterns should be. That's the process of training. It's a big amortization procedure, but you can imagine it takes a lot of data, and as many links as you have in the neural network, you have weights. So those are the parameter sets that you have to deal with. Now, the data itself, either labeled or unlabeled. And this is fundamental for the concept of supervised versus unsupervised training. Most of the stuff that we do, I think, relevant for you, will be supervised learning where your data are labeled. There are examples where you don't label the data. We'll go a little bit offline on that one if you're interested. And then there are hybrid, where it's both labeled and unlabeled. Technically, the whole ChatGPT world is the hybrid. So I'll turn a quick example to show you what totally inspired me and how powerful these are. In 1986, Janowski published a paper showing how a neural network could be taught to read a page of text aloud. No big deal today. We have Siri, we have Google. In fact, I don't know if you know, in your iOS 17, you can actually train it on your voice, have a personal voice now. Pretty amazing. But this neural network was new. It could take a stream of text, and for the centered letter, in this case the C, it was trained to produce how that C would be sounding in a phonetic sense. And the C, depending on the context, what preceded it and what followed it, could be forced, the neural network would be forced to produce that C. So if you think about that, if you take a page of text and you train a neural network on, as you slide it through the text, how each letter is sounding as a function of what came before and what followed. Once you have that neural network trained, and Janowski demonstrated this, you can run a whole new page of text never seen before, and it can produce an audible sounding description of the text and you would expect it to sound the way it did, and it actually performed quite well. This to me was just like the light bulb moment, because as soon as I saw that, whoa, let's use this for protein folding. So the one example I touch on development from my work, we used amino acid sequences as input and tried to predict features or something that might be relevant for those sequences as output. We actually were working on secondary structure prediction at first, figuring that the center amino acids in, say, a window, the residues that were preceding the residues that would follow, would help decide that that residue was in a helix or a strand or a turn. We had great results, but were sued by Janowski. They published a paper right about the time we were working on that. So we did a quick pivot and said, let's work on something different. How about benzyl by bond formation? Turns out we were able to come up with a neural network that could predict very strongly whether a centered amino acid sustained, depending on what flank did, if it was involved in a disulfide bond or not. That was pretty cool. And that was basically net talk in the context of protein folding, or in this case, a very key feature of protein structure. But quickly turn to ChatGPT. I'm not going to go through all of this, no way. But the key, this is called a transform. This is a fancy way of embedding the key blue feed forwards with different representations going in and out. And I don't know if you knew this, but all ChatGPT does, it's a sophisticated autocomplete. You give it a primer sequence. You give it a series of words as input, and it predicts what the next word would be in line. And it then feeds that whole sentence back in, and it predicts the next word. And it streams until it's done. That's pretty amazing if you think about it. In fact, the developers of this transformer model don't really understand how it works. They just know that they trained a ton of data train a ton of data, like all the text that you see on the internet, all the wikis, all the different books out there, that if you give it a stream of initial text as input, initial set of words as input, it will predict another word that then when you fed in, it can come up with like conscious thoughts. Pretty cool. But you can imagine that if you can do that, you can do a ton of different things, but keep in mind, the number of parameters these neural networks use is ginormous. ChatGPT 4 has 1 trillion parameters that have to be trained on. So that's why if you're a stockholder of NVIDIA, you've been doing well, because NVIDIA produces the GPU systems for the computer systems that need to be trained. But at the end of the day, compute power is not going to be the limitation. It's going to be the time. We learned this years ago, and it's still true today. You can't trade on Twitter because 1% of it is actually useful. You know, you can't trade on data that's garbage in and garbage out. The bottom line. So if you have a massive infrastructure of a neural network, you need to be able to have a large amount of data, or you reduce the infrastructure of the neural network down substantially. With respect to Pichia, it's why I'm here and it's why I'm already over, right? Sorry. I had examples of several of these in my supplemental slides, but I'm going to just touch on one, the optimization of certain recommendations, because this is just one of many. But you can imagine, from what just I've described so far, you could use these technology, and many have already, to optimize sequences towards certain desired expression, methanol utilization. You could use it for summarizing documents and writing reports for you in the ChatGPT world. You can use it in the bioreactor design, process monitoring. I think some other talks going to go into that. But so I want to turn to one example, competitive one. I'm not sure many people are working with E. coli here. But in 2012, this group nicely published the use of a neural network that optimized 3 parameters, temperature, pH, and stir rate, to try to maximize the production of HTOP, the human soluble chemical methyltransferase. Now, they use the CCD, the standard statistical methods, to come up with a training set, basically. And this is, I can't see in the back, this is predicted versus real. And the predicted is what the neural network would produce. They calibrated it on a set of data using your statistical sort of broadening method. And they pulled some examples out that they didn't train on. That's what the validation set was. But once they trained the neural network, they pushed it to its limits to say, what can you extrapolate out? Let's try to maximize the HTOP activity. And that's what you see in the red over here. You got the neural network to extrapolate beyond what your traditional statistical methods could do. So that the E. coli folks did that in 2012. We have done. The Pichia folks jumped in, unfortunately 3 years later, but they jumped in. A tougher problem because it's membrane bound now. But they, in this case, optimized 3 different conditions: temperature, gamma SOM, and methanol rate. And again, you can CCD, central composite design, basically build a data set to train on. But then they pushed it again, the limits, and you can see again, they were able to push to extrapolate even further. So something beyond what you might have normally done with your methods, a neural network could learn and extrapolate from the data. You notice that number of 400 is a little bit bigger previously. Pick your focus. The last example I want to show you is the one that's most exciting to me because it gets to the non-invasive approaches to things. I'm a big data guy. I use neural networks for everything. I'm wearing wearables. I'm trying to capture all this information to maximize my sleep. I'm just all over this. You know, I'm wearing continuous glucose monitor, all that stuff. But the reality is you can't pull from the system without disturbing it unless you simply take a picture. This is an example of a group that used a non-stained, simple pictures, the morphology, shape of yeast, and trained the neural networks using actually a convolutional neural network, but trained the neural network to predict the level of ethanol. That's pretty cool. You look at a shape and you see what percentage of ethanol. And I think this group was able to predict as far as 30 or 60 minutes in advance of what the ethanol production would be, just based on the shape. I don't think humans could do that. I certainly can't look at yeast and say else. This is how much ethanol is there. But you can imagine if you have this capability, you could put this in a system where you're not disrupting the system. Take a picture and letting it run till when you think it should stop. Pretty cool concept. So I sped through that. I just want to lay this out here, and hopefully during the question and answer or afterwards, I'll hang around for the rest of the day. If you have certain problems in your space, in your world, that you want to make more efficient, you want to do things for less money, you want to just succeed, and you're having challenges with, if there's ways to represent your problem in terms of a data that are basically strings of numbers, input and output patterns, I'm fairly convinced you'll be able to leverage this device. As I showed before with open source, it's not going to cost you a lot of money to do that because, like I said, hire someone intern for you. So with that, I don't know if I have time for questions, but yeah, I one or two if you have them, or pop to the next speaker. It's up to you, Canoe. So thank you for your time. Yeah, and so the question is, can you improve beyond just simply using text, using the large language model concept, use images, audio? It's called multimodal training. And yeah, the answer is yes. One of the really cool areas, they call it diffusion, when you take an image, for example, and you noisy it up, and you train a neural network to take the noised image and you force it to predict what the clear image, and often does quite well. Now, if you add additional information into that, like, well, that image is a cat or a dog or a sick cell, you can leverage the imagery that's annotated. Now, if you have anything like even audible, like sound like that it's making, that's a waveform that can be represented numerically, and that can also be added in the equation. So you can go video, text, all those, and that's what you're starting to see. Pretty incredible. Basically, all the senses that we have as humans, you can think of as inputs, and it's represented into numerical representative.